So welcome everyone to the Applied Topology online seminar. So today we're doing an interview series, and the interviewee is Professor Kathryn Hess, and she's going to be interviewed by Peter Bubenik. So Peter Bubenik graduated from Toronto in 2003, and then worked as a postdoc at EPFL from 2003 to 2005 under the mentorship of Professor Hess, who he's going to be interviewing today. And he is currently a professor at the University of Florida in Gainesville. And he's also very important for our network, as he is the founding director, and he is active to this day as a member of the advisory committee. And he himself has made a lot of important contributions to applied topology, including, for example, his research on persistent landscapes and more generally embeddings of persistence diagrams into Hilbert spaces, as well as foundations for applied topology using algebra analysis and category theory. So now I'm going to let Peter take over and start the interview.
All right, thank you, Sarah, Henry, and Elhanan for organizing this interview series. I think it's a fantastic idea, and I've enjoyed the interviews so far, and I'm really grateful for the opportunity to talk with Kathryn today. So Kathryn Hess is a professor at EPFL. She was an undergraduate student at the University of Wisconsin at Madison and obtained her PhD at MIT. She does research in both pure and applied mathematics. On the pure side, her work is in homotopy theory, and on the applied side, she applies algebraic topology to the life sciences and to chemical engineering. She's an editor of the Journal of Applied and Computational Topology, Communications of the American Math Society, Network Neuroscience, Publications Mathématiques, Theory and Applications of Categories, and is the chief editor of Algebraic and Geometric Topology. She's a fellow of the American Mathematical Society and has been a distinguished speaker of the European Mathematical Society. And I'm very pleased to be talking with you today, Kathryn.
Thank you, Peter. I'm very flattered to have been asked to participate in this interview series. It's a pleasure to have this chance to chat with you.
All right, so let's get started. Maybe you can start with telling us about what sparked your interest in mathematics.
Sparked my interest in mathematics. Well, I mean, at first I thought I wanted to be an astrophysicist. I fell in love with astronomy when I was about 10 years old. I took an astronomy class for kids when I was that age, and absolutely fell in love with astronomy, was fascinated by the life cycle of stars and wanted to understand everything about that. And so we decided when I was 11 years old that I was going to be an astrophysicist. And then when I got to university, of course, this meant that I had to start by studying physics, and I was studying physics and math at the same time. And sometime in my junior year of college or so, when I was taking an electricity and magnetism course from the only woman professor I ever had in a math or physics course, the professor said, "Can you come see me in my office?" I said, "Sure." And I went to see her. She said, "Look, you're doing very well in my class, no problem. But the reason you're doing well is because you're a very good mathematician. You have no physical intuition. So you should just do mathematics instead." So, I mean, I always kind of liked mathematics, but I realized that, she was certainly speaking the truth, that it was a bit of a struggle for me to have the right insight to know what sort of mathematics I should be using to solve problems in physics. And so I kind of, with some relief, that I actually decided to do a bachelor's in just mathematics and not mathematics and physics. So at that point, I mean, I really didn't know what kind of mathematics I wanted to do. It was only when I started graduate school. I mean, I was convinced that I wanted to be an analyst, and only because I had an absolutely fantastic analysis professor, Walter Rudin, when I was undergraduate. And he just made me fall in love with, well, at least his view of analysis, which is more functional analysis. And then I got to MIT. I was like, okay, I'm definitely going to study analysis, and realized within 1 week that was not what I wanted to do. And I'd taken an algebraic topology course just to see what it was. And within approximately the same amount of time, realized that was what I wanted to do. It fit my brain. So there we are.
So that was at MIT. So you just, so how did you choose your advisor, David Anik?
Well, he taught the first year algebraic topology course that I took. And I really liked his way of thinking. It sort of fit my way of thinking. And I decided that he was the one I wanted to work with. And so he was very young at the time. He was still, I think he was still just an assistant professor. And he had only one other student at that point, who was Mark Hovey. And so he was happy to accept me, I think. And it was very, very good to work under his supervision.
So can you tell us about your experiences as being a young woman in a graduate math program?
Well, at the time, right, we're talking about the mid to late 80s. There were even fewer women in mathematics than there are now. I remember the very first time I went to a big conference, big algebraic topology conference. It was at Northwestern in 1988. Big conference, maybe 150, 200 participants. And the first morning you go in and everybody's having donuts and coffee, right? And I went in with Kathryn Hess, who was one of the other MIT PhD students at the time. And we walked in there and we looked around, and like 80% of the people in the room were bearded guys wearing checked flannel shirts. And I thought, what are we doing here? Are we really going to, how can we fit into this environment? It was a little bit overwhelming at first. And then, you know, there weren't very many of us, but there were enough that it was okay. And most of the men were very welcoming. So I didn't really seem to notice whether they were men, women, whatever.
Yeah, so I guess you and Kathryn have both continued on to successful careers. So did you consider other possible careers as a graduate student than academic career as a mathematician?
Well, there was one point. I mean, my first semester at MIT was very hard. It was there were, in the sense that there was so much work to do. It was there really, you know, I think a lot of people go through questioning phases when they're starting out. And I definitely did. I definitely went through the, oh my God, do I really belong here? Am I really going to be good enough? Am I going to be able to do research and so on? And you know, I went back to stay with my parents after the first semester at MIT, and I thought, do I really want to go back and continue a doctoral program in mathematics? I seriously considered maybe trying to switch into linguistics because I was really fascinated by linguistics. But in the end, you know, there was still the pull, the draw of mathematics, and I went back to it, and it got easier. And but there were a number of times in my career when there was when I was sort of forced to take a break, like any time when I was on maternity leave after one of my children was born, I always went through this sort of questioning phase. Is this really something I want to go back to when this is over? And I think it's really good to give yourself the time to do that, because if you allow yourself to think through what else could I do, what would I rather be doing, in the end you decide, no, I really want to continue doing what I have been doing, then you go back to it, you know, sure that you're really on the right track and with added enthusiasm and interest for what you're doing.
So in your research, you spent most of your time on the more theoretical side of algebraic topology, most specifically homotopy theory. Many people in the audience might be most familiar with your applied work. For those people, can you tell us something about homotopy theory and why it's an exciting part of mathematics?
Well, I really love the way that homotopy theory gives you a very interesting perspective on topological spaces, where, you know, you're interested in topological spaces up to continuous deformation. And I like the fact that it's something that can allow you to take problems in topology and transform them into problems in algebra that maybe you have some chance of solving. And so my original roots in pure algebraic topology were in rational homotopy theory, which is where you're considering topological spaces up to rational equivalence. You're forgetting all of the torsion, and you're just thinking about the non-torsion part of the spaces. And everything becomes much easier. I mean, it's not easy, but it's much easier once you've forgotten the torsion. And you can actually translate problems in topology perfectly into problems in algebra, and then translate the results back into topology. And I found that fascinating. And I really loved working with some of the algebraic tools that were available in rational homotopy theory. And sort of starting a rational homotopy theory, that got me interested in what are called model categories, which is a sort of an abstract way of saying, like, what actually do you need in a category in order to do homotopy theory? Like, what are the key tools, the key that you need in order to be able to talk about a notion of homotopy equivalence and to be able to do the kinds of constructions you're interested in homotopy theory? And so I went more in the direction of pursuing that kind of abstract homotopy theory, and which has, you know, deep connections to category theory and so on. And it's a really beautiful area, in my opinion. And I really like the way that you can sort of take a step back and have a view of, you know, analogies between different kinds of constructions in different parts of mathematics, things that are homotopy-like, and be able to sort of prove theorems in this more abstract context that then have specific applications within concrete situations, specific situations. And particularly, for example, to have a version of Galois theory, but in this homotopy theoretical context. This is something I've always been fascinated with. Galois theory is such a beautiful part of algebra. And then to see analogous structures in homotopy theory is really fascinating, in my opinion.
So, you established your career in pure mathematics, and I think you certainly could, and you continue to work in that area, and you could have just done that. And at some point, you got interested in applied mathematics. Can you tell us how that happened?
Well, for quite a while, I've been interested in at least some applications. In fact, the original reason that I started thinking about applications at all goes back to when I was been at EPFL for only a couple of years. And at one point, I'm not quite sure why, the president of EPFL asked to speak to me. So this is way back in the mid-90s or something. And he said, you know, if you want to have any chance of having a longer career at EPFL, because EPFL was very much more engineering and application oriented at the time than it is now. It's much broader now than it was at the time. He said, you know, you should think about whether there's some interesting applications of the kinds of pure mathematics that you're doing. And I thought, well, and so I did some poking around and saw that, hey, you know, they could do some interesting applications of knot theory when studying polymers and such. And so actually supervised a PhD thesis about applying knot theory into polymer physics. That was interesting enough that the PhD student in question was hired by a polymer physicist for her postdoc. So that was my first indication that maybe topology, not algebraic topology, in the sense of knot theory, but could have some really meaningful applications. Then back around the late 90s or so, I started thinking more about possible applications of algebraic topology in computer science. So this was the direction that was developing, for example, with Lisbeth Weisskopf and Martin Rausen and Eric Goubot, people like that. And got interested in that area, and that was why in the end I participated in the first ATMCS conference back in, I think it was 2001 at Stanford, and heard about barcodes for the first time then. And so I've always been sort of touching various possible applications. I really love pure algebraic topology in and of itself, but I've always been fascinated by what sort of applications it might have. And then in the, I don't know, maybe 7 or 8 years ago now, when it became clear that TDA had some deep applications. So with the work of Gunnar Carlson, Monica Levine, and others on the breast cancer, for example, and you sort of say, okay, well, this looks like we could have some significant applications of real interest in biology, for example, I decided it was time to start looking more deeply into it. And also, I mean, I've been thinking for a while about how one might be able to apply topology to neuroscience. This is a conversation that Ron Levy and I've been having with neuroscientist Henry Markram, sort of for fun, since about 2005. And it suddenly became easier to imagine actually looking into real applications of topology in neuroscience in various ways. And so sort of a lot of things came together in around 2014 or so that we could actually start applying some of these, doing some real mathematics in real neuroscience. It wasn't just toy examples anymore.
So this is your work that's part of the Blue Brain project.
Exactly.
Can you
So
maybe tell us a bit about that project and what, so you now kind of have a laboratory in neuroscience and what part that plays in the project, and maybe also how it is working with kind of collaborators outside of mathematics in a large project.
Sure. So I'll start by talking about the Blue Brain Project. So the Blue Brain Project was founded around 2004, 2005, something like that, by Henry Markham, who's a neuroscientist, came to EPFL from the Weizmann Institute with the goal of building digital reconstruction, so reconstruction on computer of, well, as much of the brain as possible. Starting with the brain of a rat, because there was more data available for rats than for many other kinds of animals. And starting with a very small part of the brain, just what they call a microcircuit, a small sort of core sample of the somatosensory cortex, which is that part of the brain that's responsible for processing incoming sort of touch information. And so it took them about 10 years to build a really good digital reconstruction of this model, taking into account like data that they gathered from many laboratories, by doing an intensive search in the literature and getting various wet labs to do actual experiments to find data about connection probabilities between neurons and the shapes of neurons and all this sort of thing. And they did this complex algorithm to build this digital reconstruction of the brain. And this thing was more or less ready in 2014. And this is why this became the moment at which we could start to apply topology in this context, because here we had a model of part of the brain with roughly 31,000 neurons with roughly 8 million connections between them. And so you're looking at, basically you're looking at a very large directed graph, and with perhaps weights on the edges if you know something about how strong the connections are. And it's like, all of a sudden, this is a mathematical representation of part of the brain to which you can start applying tools from algebraic topology. So that's where both Ran, Levy, and I started collaborating very closely with people at the Blue Brain Project at around that time, and started writing papers with the people there on the projects. And I also collaborate with other EPFL neuroscientists on other kinds of projects that usually involve sort of more standard applications of TDA to the various kinds of data that they have. In my experience, the people in the life sciences are very interested in collaborating with anybody who has new powerful methods for data analysis. They really, because they're creating so much data, and just making any sense of it is, they're eager for help and very open to discussing with people from TDA, from mathematics in general. Just, can we help provide any insight into the data that they've gathered? So, I mean, working with people from other fields, requires a certain amount of effort, because you have to learn their language, you have to understand what is important in their field. You may be completely wrong about what what you think is important, may be completely different from what the specialists think is important, and you need to be respectful of their domain knowledge. And your beautiful mathematical model of how things should be is usually not how things are, and so you need to be very open to discussion and to listening to your collaborators, and also to make sure that there is a continuous feedback loop. They can come to you, say, we have this kind of problem. You say, can we model it this way? No, we have to change this. It's really about dialogue, and it's about investing in learning enough about the domain that you can actually have an intelligent conversation. And usually I find that they make at least some effort to try to understand the language of, like, what's a simplex and what basically are we measuring with homology and so on. So it's really, I find, a great pleasure collaborating with people from other fields.
So what about it is kind of most rewarding, and also what about it, that process, is the most challenging?
So what is most rewarding, I think, is that, in the cases where it's turned out that TDA or topology more generally has provided real, significant new insight into some problem in biology, or in one of the other projects I worked on in material science, then that's extremely satisfying, I find. It's like, wow, we really helped in the discovery of something new in the field, and the people who work in that field actually care about the result. And particularly if you find something surprising, then it's even more rewarding, I would say. And what's hard is, investing enough that you can understand what the problems are, what the parameters are, and also just continuing making sure this feedback loop with the domain specialists is working. I would not say it's unpleasant, but it's work.
So in addition to your work in neuroscience, one of your other successful applied projects is in materials research in studying nanoporous materials. Can you tell us about that project?
I think I've told this story many times. I think it's a great story, so I'm very happy to tell it again. So I had a new colleague who just arrived at EPFL from Berkeley, and every year at the beginning of September or so, there's a professorial retreat for the EPFL professors to go somewhere, some nice hotel in Switzerland, and spend a couple of days talking about issues related to teaching and research. And it's also an occasion for the new professors to meet their colleagues and start to become integrated. Well, we were at one of these professorial retreats in Lucerne, and I was standing in line for the buffet lunch on the first day. And one of the new professors was standing in front of me. And knowing that he was one of the new ones, I thought, well, I'll introduce myself. So he starts to get to know some people. And he said, oh, well, what's your field? I said, I'm a mathematician. And as all mathematicians know, that's usually the end of the conversation. Even among scientists, they say, oh, a mathematician, okay. But then he said, oh, what kind of mathematics? And I thought, okay, that's, I knew that he was a chemical engineer or a material scientist. And I thought, well, okay. I said, yeah, I'm an algebraic topologist. Oh, topology, that's exactly the kind of mathematics that I need. And I was like, what? And so that started a conversation about these nanoporous crystalline materials and his intuition that it was really the topology of these crystal structures that was important for their performance properties, like how good they are at methane capture, CO2 capture, these things that are very relevant these days. He said it depends. It doesn't, at least in the case of the very simple crystals of zeolites, which are just built from silicon and oxygen, there shouldn't be any dependence on anything else. It's really the topology that counts. And so he'd worked together with people at Stanford for a little while, and they had some indication this was the case, but it wasn't really conclusive. And so he wanted to take this further and really, really develop it. So we ended up talking for more than an hour at lunch that day. I almost missed the next session of the professors' meeting, and started a collaboration that later involved as well Pavel Blotko and others. And it meant led to the development of this new approach to studying these zeolites by looking at an associated persistence diagrams and various trees. And yeah, it provided a really nice way of doing, broad sort of being able to scan the huge quantity of possible zeolites and find which ones would be worth examining more closely to actually synthesize for these kind of performance properties. That was an exciting project to work on because it really led to something concrete.
Very cool. Yeah, maybe we can take a moment to step back. So we've kind of talking about what you've done now, most recently, and earlier on we were talking about kind of your time as a graduate student. So for the many kind of graduate students and young researchers in the audience, can you tell us about your journey of from a graduate student to a full professor?
Okay, so mine has been quite atypical, right? So while I was a graduate student, I applied for one job. Basically, because I applied for, there was a postdoc that was available from like the Swedish NSF to go spend a year at the University of Stockholm. And I really wanted to go spend a year in Stockholm because, I mean, that there was, for mathematical reasons, there were people who were doing local algebra there. It's very closely related to rational homotopy theory. And I really just wanted to live in Sweden. So I wasn't really thinking about things from a careerist point of view at all. I mean, I I'm sure that if I hadn't gotten that fellowship, I would have applied for other jobs, but I knew before Christmas when I was beginning to be graduating in the summer that I had that fellowship. And so that was it. So not typical. I realized I was very lucky that way. And then after that, I had a couple other postdocs that they were people basically, colleagues from National Homotopy theory who invited me to come spend some time with them in Nice, in Toronto with Steve Halperin, the crowd that you knew when you were a PhD student there, although Steve was no longer there when you were there. And so the last year I was at MIT, I met my husband who is Swiss, and we decided we were going to try to live in Switzerland, try to find a place where we could both work. So he works in industry, and so we didn't have the two-body academic problem. But I just had to find, Switzerland is not a very big country. There aren't that many universities, and so finding a postdoc in Switzerland was not something that was obvious to do. So back in the day, of course, we didn't have the internet. So I went to the library at the University of Stockholm while I was there and pulled this thick book off the shelf called Who's Who in World Universities or something like this. And just looked, okay, what are the universities in Switzerland? What mathematicians are there? And I just wrote to a bunch of mathematicians to say, hi, I'd like to live in Switzerland. This is who I am. Here's my CV. And ended up going and having some interviews, and I got a postdoc at EPFL. So I took that postdoc at EPFL after being in Stockholm, Nice, and Toronto in that order. And so started off as a postdoc there. And at the time, there wasn't a tenure track at EPFL as there is now, but there wasn't at the time. And so I just, it was possible to sort of eventually have a permanent type position with an instructor type title, or then it was something called titular professor. And it was then really when I started doing the applied topology as well, that I moved on to a more standard track and became an associate and now a full professor. So it's been a complicated and kind of weird career path. So, because I never really was very careerist about it. I just I was doing what I was interested in doing, where I was interested in doing it. And I was very lucky that it worked out.
I see. So a lot of research universities have a kind of institutional bias against promoting people who have been postdocs there. And so Vanessa Robbins gave one of the previous interviews, and also kind of for family reasons, she had decided she wanted to be in Canberra, and she talked a little bit about her difficulties in kind of getting a permanent position there. Yeah. So was that—
You end up being kind of taken for granted, right? Because they say, oh, well, she's got kids, the kids are in school here, her husband has a job here, we can just take her for granted. She'll always be there. So
is that frustrating? I imagine.
Yes. Yeah. No, but things worked out in the end. I was lucky that things did work out. They could have worked out earlier, but I really, I made the decision that for family reasons, this is where I wanted to be. And
yeah, so I think there's lots of people who are kind of in that position. Would you have some advice to give?
Don't lose faith. It's when the time seems right, raise your hand and say, hey, don't forget about me. Here I am. Don't take me for granted. Look at what I'm doing for you. Look at what I've accomplished. Because people might not pay that much attention to your accomplishments if you're just there. You're part of the furniture. And so sometimes, women in particular are taught not to boast or brag, right? And not to they hide their lamp under a bushel, as they say. And I think that maybe particularly for women, it's important to say, hey, take the bushel off and say, look how bright this lamp is. But also one thing that I think is important is that that it's important for for universities to take into account different kinds of academic trajectories, in the sense that, you know, I know there are women who manage to have young children and continue producing at the same rate, and I'm admirative and astonished they managed to do so. Because I know that when I had, you know, 4 children, 10 and under, I managed to do my teaching, supervise my graduate students, do a little bit of research, and that was about all that I could really manage. But then there's this sort of magic thing that happened, or happens, or at least happened to me, and I know it's happened to other women as well, that when you reach the point where your children no longer need so much of your time and energy, all of a sudden there's all this research energy that's been pent up for a number of years that gets a chance to explode. And it's like, you know, you finally have, you're so excited, you're so relieved finally to have time to concentrate on research, that it's a magical period. And this happens, I think, to a lot of women, that they all of a sudden they have this burst of productivity after their children are no longer so young. And I think it can pay off for universities to be a little patient while women have young children. And you can pretty much expect, I think, that once they have, finally, they're so eager to get back to it, the chance to do research again, that they'll be remarkably productive.
So can you say a bit more, or maybe give advice on kind of other young researchers on kind of finding time for research, and also making best use of your time for advancing your career?
So I guess I should preface this by saying that I respect extremely much the people who have had young children at home with them for the last 18 months because of the COVID pandemic. I cannot imagine how hard it must be to have tried to get anything done, much less serious research, when also having young children at home, homeschooling and whatever. Under more normal circumstances, when children actually spend some time in school and you have some. So I think it's one thing that I did when my children were still young enough that it was hard for me to get much work done at home, was every so often, particularly when I was in the phase where I really wanted to advance on writing a paper, I would say, okay, today I'm just staying at work as late as I want to. I mean, sometimes until late at night, just so I could push and try to get this paper done. And just having that time when I could just be completely focused was so precious to me that it really, really helped a lot. So every so often to be, you know, selfish and say, I'm going to take this entire day, nobody bother me, I'm going to work. It's important to do that for yourself every so often, I think. So yeah, it's not easy, for sure.
Thank you. So at EPFL, you're a board member of the Women in Science and Humanities Foundation. Mm-hmm. And we've talked a little bit about the challenges of being a woman in mathematics. Can you maybe give some advice to some of the young women mathematicians in the audience, and also more broadly discuss how to best encourage participation and retention of women in mathematics?
So that's the $1 million question, right? I mean, and that extends, you know, now beyond women to many other underrepresented groups. But I'll talk about women since that's what I know best. So one thing that I think works very well for retention of women, and this I think has been more or less demonstrated now, are these research networks for women that started being developed in a little before 2010, I think, by women in number theory. We created these workshops where women get together and actually do research together and write papers together. And in this way, you create networks, you create natural mentorship relationships. And not just, oh, I'm signing up to be your mentor, but I'm a senior mathematician working with a junior mathematician on a paper. And so we naturally have a kind of mentoring relationship that evolves from that. And so together with Brenda Johnson, Maria Bastara, and Christine Bauer, we set up a network like that for women in algebraic topology. called Women in Just Topology, because it's sort of better, it sounded better as an acronym. But we started running it in 2011. We had the first workshop in 2013. And ever since then, there've been workshops every 3 years where women form these groups with usually 2 senior team leaders and then 4 to 5 junior members who work together for several months by Zoom or whatever, remotely until they meet for a week. All the groups meet together for a week. First couple of times it was in Banff, then it was at the Hausdorff Institute in Bonn, to finish up the project, and then they all write a paper together. And the first time we did this, we were like, well, is this actually, people are going to do research together, but is this actually going to lead to something that's going to be publishable? And this was the great thing, that every single team produced a paper that was more than worthy of publication. And there was a real gamble at first, but now we realized, hey, this really works extremely well. And a lot of the papers that were produced by this have then, the groups have continued collaborating, or some subgroup thereof has continued collaborating, and there were lots of offshoots. And so that's been very productive research-wise, but also the effect of getting young women integrated into a network when they're still PhD students or postdocs has, I think, made it easier for them to stay, because we've noticed considerably higher retention of women in algebraic topology since then. The number of women who now hold tenured professorships, women algebraic topologists who hold tenured professorships in the US has just, I think, gone up by a factor of 10 or something in the last 10 years. I mean, it was very small to start with. So it's the first time we organized this, we had to actually reach out. We wrote to a lot of colleagues they had and said, do you have any PhD students or postdocs whom you could recommend for this program? But now there are so many that, they have to apply, it's competitive to participate and so on. So it's really, I think, a model that has proved that it works. And I think that there's more than just having an event where women get together and talk about what it's like being a woman in mathematics. It's women who get together and do mathematics together. And that way there's the community building, there's the mentoring, and also just showing that, women can do great mathematics together. So, and the Women in Computational Topology does something very similar as well. I'm not as aware of how that has affected the population of women researchers in computational topology. I imagine it's had the same effect, but I think that this is something very concrete, very positive that one can do.
That's fantastic. Thank you.
Welcome.
So you've received numerous teaching awards, including 2 awards for the best teacher at EPFL. Can you discuss the kind of the importance of oral exposition, both in teaching and in research?
Oh yes, well, thanks for mentioning the awards. Teaching is something that's extremely important to me. I think a lot of what makes a good teacher is really caring a lot about teaching. Oral exposition is extremely important, and I think that this is a really important lesson for young people as well. That the first impression that you're going to make on a hiring committee or a potential supervisor, postdoc supervisor, is when that person hears you give a talk. Almost certainly, maybe on Zoom these days, maybe in person sometime in the near future. We can always hope, but it's really, really important to learn how to give very clear talks that well motivated, lots of examples, and just always trying to bring your audience along with not necessarily to impress your audience, but to share with your audience. And I think that for me, it's wonderful if you can prove marvelous theorems and do great mathematics, but it's extremely important to be able to communicate what you do, both in clear written form and in oral form.
Very good. I completely agree. So we're nearing the end. So maybe you can tell us something about the projects that you're currently working on, and maybe say something about what big ideas you're most excited about.
Okay, projects that I'm currently working on. Let's see. Well, just finished up a couple of projects. One One that was with the team that I worked with for Women in Computational Topology on thinking about directed graphs and good ways of measuring, putting some kind of metric on the set of directed graphs. So this was motivated by project you did with the blue brain, where you take the directed graph underlying this network of neurons and associate to it this directed flag complex, which is like a directed version of the usual flag complex or click complex, and then compute homology and count simplices and whatever. And these turned out to be sort of meaningful variants from a neuroscientific point of view. And so, but it's kind of expensive to compute homology. So you're thinking about, well, how could, are there other, if I know sort of the homology of one network and I know another one is close, are the homology of the directed flag complexes going to be similar and things like this? And so this was a preliminary exploration. We were looking at different kinds of distances you could define on the set of directed graphs, and which ones really were sort of more similar to the notion, the distances that you could define based on homology, based on Betty numbers and simplex counts and such. So that was a fun project to do. And then one sort of long-term project that we're working on is related to the questions of neuron morphology. So neurons have a wide variety of shapes. And because a neuron's shape influences its function considerably, it's important to be able to classify neurons by shape. And so together with Lida Canary, Van Levy, Pavel Botko, Martina Scolmero, and others, we developed quite a simple TDA tool called the topological morphology descriptor you could associate to a neuron that then produces a barcode, or persistence, some sort of persistence landscape, or whatever you want to use as input to machine learning, that you can then use to classify these neurons, and it worked extremely well. And then primarily Lida Canary developed a method to sort of run the machine backwards, starting with a barcode, sort of synthesize neurons from these barcodes. And in a way that actually produces a population of synthetic neurons that is very close in some well-defined sense to an actual biological population. And then Lida and Adélie Guérin and I thought about, well, how can you, what is special about the populations of biological neurons if we look at their barcodes or the distributions of barcodes, or if we sort of do the process of associating a barcode to a neuron and then generating a whole population of other neurons from this using the synthesis algorithm, what can you say about how different this population is from the original neuron, things like this. And sort of approaching things more mathematically by thinking about how to associate a permutation to these barcodes and so on. Anyway, sort of getting closer to thinking about things called maybe combinatorics or geometric group theory and so on. And so this is being pushed even further. Particularly, there's a collaboration with Justin Curry and Adélie Guérin where they're working and pushing along in this direction. And I think there are going to be some really interesting results tying together some things in algebraic combinatorics, maybe some things in operator theory, maybe some things to this whole question of distributions on barcodes. And I think there's a really rich area of research that can go on there with the relation distributions on merge trees compared to distributions on barcodes, and what the relation is to the symmetric group and the Coxeter complex. And there's some really cool stuff that's going to come out of this. Also working on other applications of TDA to studying not only populations of neurons, but populations of what are called microglia. So these are basically the immune cells in the brain. And so they're the ones who come to the rescue when there's some infection in the brain and such. And seeing how, together with a team from IST in Vienna, taking their data where they've made beautiful tracings of microglia and using these topological type tools to study populations of microglia and see how they evolve as the animals age or as they develop various pathologies and so on. So that's cool. And one thing that's neat about it is it showed that there's actually a difference between males and females, which was not something that people knew about until you started looking at it. This was sort of topological lens. So there are other applications like this of topology and neuroscience that are interesting to think about. And as with respect to the Blue Brain project, now we're thinking about plasticity in the network. So as you learn, the connections between neurons become stronger or weaker, or can completely disappear or appear, whatever. And you can study this evolution of the network also using topological tools, but now more like persistent homology, because you're looking at how you have a weighted directed graph, and you can associate to a weighted filtered simplicial complex, and you have filtered simplicial complexes that are evolving through time, and you'd like to see, find some kind of structure property relationship between the persistent homology that you're getting like that and some property of the network in terms of preference for certain stimuli or whatever. So this is research we've been developing with the Blue Brain project for a number of years. It took them a while to get to the point. This is one thing you need to, oh yeah, I should have mentioned this earlier. One thing you need when you're working with people in other fields is patience, because it can take a while for the experiments to be done or even to be ready to be performed. And this was this case. We've been planning these experiments for 3 or 4 years, and finally we can run them. And so we're going to see whether we can use these topological tools to discover interesting structure property relationships in the case of synaptic plasticity. So, yeah.
Those all sound really exciting. Yeah, so maybe we can end, but if you can answer, I'll give you maybe a simpler question. Can you tell us about this beautiful background that you have behind you?
Oh, so that's the Jungfrau, which is one of the, probably one of the most famous mountains in Switzerland after the Matterhorn. There are the three, the Eiger or the Münch and the Jungfrau, which are 3 mountains that are all next to each other in the Bernese part of Switzerland. And I was lucky enough to spend a week in that area on vacation at the end of July and did some marvelous hiking. And I think this is, in my opinion, one of the most beautiful mountains in Switzerland. So yeah, I feel lucky to live in such a beautiful country. Having to be confined in Switzerland, yeah, there's a lot worse.
Well, thank you so much.
Yeah, I was going to say thank you so much, Kathryn, and we'll move on to the questions. So go ahead.
Okay, thank you, Peter. Thanks for a really fun interview.
Thanks, Peter and Kathryn. So I have some questions now that have been chatted in from the audience. So I'll go ahead and ask those. I think I have about 5 questions or so. So I don't think we'll go past the hour, if that's okay. So the first question is from Hanka Krimska. So how important is coding in your job or in the job of postdocs or graduate students in your group? And related to that, how do you see the recent progress in technology influencing research mathematics?
Okay, so to be perfectly honest, coding is not part of my life because I never had to code until I started working in applied topology. And at that point, I had PhD students and postdocs who could do the coding. And so it's extremely important for them, however. I mean, I think that I would strongly, strongly, strongly encourage anyone considering possibly going into applications to learn how to code. I think it's really important. I regret that I do not know how to do so. I'd been planning on using this spring to learn how to code finally in Python, but then I became Associate VP for Student Affairs at EPFL, and that went out the window. So, and then the other question was, I'm sorry,
just if you have any further thoughts on the recent progress in technology and how that's influencing research done in mathematics.
Well, I think that certainly there have been new interesting questions that have come up in algebraic topology and homotopy theory, inspired by what people have seen in applications. And also, I think that, for example, there's a spate of research now into sort of more directed things and coming from directed graphs and so on. I mean, there was already some directed algebraic topology arising from computer science, but it wasn't quite the same thing as what we need when we're thinking about these sort of directed graphs, where we want whatever topological invariance we develop to sort of reflect the dynamics that can happen on a directed network, which was not what you were getting from the invariants that were from directed algebraic topology before. And so there's an evolution of new invariants that could, it's just pure mathematics, right? But that has entirely motivated by, oh, we need these for these applications. So I think there's interesting new pure mathematics coming from applications. And it's really helpful to be able to then go test and say, oh, well, let's, I think this is very interesting. I wonder if it's, always zero. So let's go run some experiments.
Question from Massimo Ferri is if you have any thoughts on potential uses of torsion in applied topology or topological theories.
Yeah, well, I mean, of course, as somebody with deep roots in pure topology, my first questions were, well, okay, yes, we're computing homology mod 2, okay, but what about torsion? And so, I mean, and we actually tried for a while with the directed graph from the Bubenik to see, is there any torsion actually in the homology? But the thing is so big that we're never able, I mean, maybe we could go back and try now. Things have gotten faster and faster over the last few years. Maybe we could actually go try and see if there is any torsion. I think that'd be super interesting to see if there was torsion. I mean, one question that we're playing around with was like, what is the minimum number of vertices you need in the directed graph so that you could actually produce torsion? And I think one of my postdocs came up with an example with 9 vertices. It might have been 10. But I think that it'd be really intriguing to find torsion in such a complex context and figure out, well, what could it possibly mean? And that, so I would love to know more about that. I would love to know more about, like, for the time being, we've been using very basic topological invariants, calculating Betty numbers. But, I like algebraic structure. I'd like to know, if I look at the cohomology, is there a non-zero cut product? Are there non-zero Steiner operations? And I think that the existence of non-zero products, non-zero Steiner operations would be super interesting and probably must have some kind of meaning. And that would be really, really fascinating.
Next question is a summary of a question from Nandan Kulkarni, who's a life scientist. So you touched on some maybe perspectives you have as a mathematician working in interdisciplinary collaborations. Mm-hmm. What thoughts might you have for, say, a life scientist who's interested in working with mathematicians?
I mean, I think that a life scientist who's interested in working with mathematicians, it'll be helpful if they're willing to. I mean, I don't think a life scientist to work with an applied algebraic topologist needs to know much more than linear algebra. I mean, of course, they all know some statistics, they all know some dynamical systems, so on. But if you know linear algebra, then you can understand the basics of homology. And I think understanding what a simplicial complex is in a very basic way is not so difficult. I mean, I've taught it a number of times to life scientists at this point, and they do catch on, and they do get the idea, and they do understand essentially what you're measuring with Betty numbers and so on. And so I think just being confident about linear algebra is all that it takes, and being willing, again, to participate in this feedback and to make sure that you develop a common vocabulary is really important.
Mm-hmm. Another question was if you have thoughts on the relationship between academia and industry, maybe from your own experiences or from experiences from others you've worked with or mentored.
So I actually work fairly closely with 2 different startups in Lausanne. So one of them is L2F, which was founded by a bunch of mostly EPFL students, and that has developed the Jodo package that you may be aware of. And it's been really interesting. So when they started out, their knowledge of TDA was somewhat limited, and I could teach them things. Now they teach me things. And it's been really fantastic to watch how they develop. It's been extremely hard, of course, to develop a startup, and especially with the last 18 months of pandemic, it hasn't helped. But to see them striving for success and realize that it's a different ballgame, because you actually have to try to make money. You actually have to try to sell something. It's not like, oh, here's a beautiful idea. Like, okay, how can I take it? How can I commercialize it? This is a completely different way of thinking. And I collaborate with another startup called Innate, which is sort of more about using some notions from neuroscience and topology and machine learning, and sort of combining it all into doing forecasting and other things like this. And again, for me, it's been a real learning process to watch how a startup develops and the kind of mistakes you can make. And like the fact that in both cases, the startups ended up sort of shifting their focus when they realized that, you need to find something to sell if you're going to survive. And that's very, very different from academia. But it's been a real enriching experience to interact with industry as well. And, I think at one point I toyed with the idea of, maybe I could sort of get more seriously into this kind of startup game, maybe not leave academia necessarily, but, and in the end of it, no, I'm really made for academia.
And one final question. What advice might you give to a young researcher, in particular a young woman researcher, aspiring to be an applied topologist who studies with who struggles with imposter syndrome?
Yeah, so do I. Maybe a lot less now, for sure. But I feel like I often went through sort of cycles of wondering, do I belong here? Is it a mistake that they accepted me into this? Like, I certainly felt like that at MIT. Was it a mistake that they accepted me at MIT? Was it a mistake? But then I think the more you go through the cycle, the more you recognize what you're going through, and you can say, okay, it's gonna get better. And when you're caught in that cycle, to reflect back on your past successes and say, hey, wait, no, look at what I've actually done. I've done this, and I've done this, and I've done this, allow yourself to be proud of what you've accomplished. It's really important. And to say, hey, it's not a mistake. If people selected you to be here, they wanted you. They weren't forced to choose you. And so you can remember that, and then also just, I suppose it's harder at the beginning of your career when you don't have that many successes to look back on, but there's always something you can look back to and be proud of and say, I did that, and I can continue to do things. I mean, I think it's probably hardest before you've actually done your own independent research for the first time, actually proved your first theorem, or actually, run your first experiment and analyze the data and extracted something interesting. I think that's, am I going to make it? It's a question we all ask, but I can remember clearly the moment sitting in the math library at MIT and thinking, my God, am I ever actually going to be able to prove my own theorem? It's intimidating, and nonetheless, lots of people get there, and so can you.
Well, thank you so much. We really appreciate you sharing your perspectives. And now let me pass it back to Sarah to close us out.
Sorry. Yeah, thank you so much again. So I think with this, we're gonna stop the recording and